this lecture we continue our discussions on first order logic that we started in the previous lecture. In the previous lecture we ended by introducing two quantifiers, namely universal quantifier and existential quantifier. We also listed down some propositions involving these quantifiers, namely universal and existential quantifiers and predicates. So, this is continuation of first order logic. We are discussing two quantifiers, namely existential quantifiers and existential quantifier and universal quantifier. Now, I list down some statements involving these quantifiers. The first one is for all x f x. Now, if this proposition is true, that means for all x in the universe the predicate f x is true. So, we write the abbreviated meaning as all true. Next, there exists x f x. If this statement is true, that means there is at least one x such that f x is true. So, we write the abbreviated meaning as at least one true. Third, I write quickly not of there exists x f x. This means none true. Fourth, for all x not of f x. That means all false. Fifth, there exists x not f x. This means at least one false. Then not of there exists x such that not of f x. That means null false. Then not of the for all x f x, this means not all true, and lastly not all false. Now, we have seen these propositions in the last lecture. Now, what we can do is that to group these propositions into equivalent propositions. For example, all true and none false. All true is for all x f x, and none false is negation of there exists x such that not of x is true. So, all true and none false should be same. So, they are equivalent. Now, our question at this point is that can we, by using the rules of logic that we have developed, derive the equivalence of these two propositions? The answer is yes, but we will do that after we have grouped these 8 propositions into 4 groups. So, here we have all true and none false. Another 2 propositions are all false and none true. All false is given by for all x negation of f x, and none true is given by negation of there exists x f x. Our common sense says that they should be equal, but the question is that how do we prove it analytically? The fourth one is not all true. So, that is negation of for all x f x. So, this is not all true, and on the other side we have at least one false, that means there exists x not of f x. Again we expect them to be equivalent, and finally we have not of for all x not of f x which is not all false and on the other side we have there exists x f x, that means at least one is true. We expect them to be equal. Now, the question is, how do we prove these equivalences? To do that, we go back to De Morgan's laws. Now, De Morgan's laws says that if I have two propositions P and Q, then P and Q naught is equivalent to P naught or Q naught, and naught of P or Q is equivalent to naught of P and naught of Q. If we look at the proposition, there exists x f x. This proposition is true if, when x varies over the whole universe, we find one instance where f x is true. Now, let us try to understand this by restricting the universe to something very small. Let us suppose the universe U consists of only 4 elements. Suppose U is equal to A, B, C and D. Therefore, we see that when I say for there exists x f x, this statement is equivalent to stating that f a or f b or f c or f d. The question is why? The reason is what I have already told, that the statement in the right hand side is going to be true if there is one instance for which f x is true. Now, there are only 4 possible instances, and for each of them I can put the value of x in f x. So, then I will get f a, f b, f c and f d. f a, f b, f c and f d are propositions. So, if at least one of them is true, then the proposition in the right hand side is true, and well, proposition in the left hand side is also true, and it is false if and only if all f a, f b, f c and f d are false, and that will also mean the left hand side false, because there will exist no x for which f x is true. Therefore, these two propositions are same. Now, on the other hand, if I have something like this for all x f x, then this is equivalent to f a intersection f b intersection f c sorry, we call it and FD. Now, let us look at the first expression that we started with, that is for all x f x and not of there exists x such that not of x. Now, suppose I start with this proposition, not of there exists x not of f x. This is equivalent to not of f a or f b or f c or f d, restricting the universe to just the set A B C D. Now, we can use De Morgan's law and write that this is equal to not of f a and I am sorry, I have to make a small change over here. This will be not of f a or not of f b or not of f c or not of f d. Now, if I use De Morgan's law, I will get not of f a yes and not of f b and not of f c and not of f d this, and since I know that not of f a is f a itself. So, this is same as f a and f b and f c and f d, which is same as for all x f x. Thus, we have established that for all x f x is equivalent to not of there exists x not of f x. Now, we will prove the other equivalences that we have stated in the beginning of this lecture. Let us consider the equivalence for all x not of f x not of there exists x f x. Again, we are restricting our universe to just 4 elements. A B C D, there exists x f x is equivalent to f A or f B or f C or f D, not of there exists x f x is equivalent to not of f A or f B or f C or f D, which is equivalent to, by De Morgan's law, not of f A and not of f B and not of f C and not of f D, and which is of course equivalent to for all x not of f x. If we take up the next equivalence, we start from not of for all x f x, which is equivalent to not of f A and f B and f C and f D, which is equivalent to not of f A or not of f B or not of f C or not of f D, which means there exists x such that not of f x. And the last one, not of for all x not of f x is equivalent to not of not of f A and not of f B and not of f C and not of f D, which is equivalent to f A or f B or f C or f D, which means for all x f x. Thus, we see that we can prove many equivalences involving the quantifiers by using De Morgan's law. Next, we move on to describing some more proof techniques by using the quantifiers. One technique is proof by example. To show there exists x f x is true, it is sufficient to show f c is true for some c in the universe. Second technique is proof by exhaustion. To show for all x not of f x is true we choose to show that in this case we have to show for all x such that not of f x is true, then in order to show that so here we have to prove that for all x not of f x is true. In order to do that, we may choose to exhaust all the elements of the universe and prove that f x is false everywhere, and that will prove the proposition for all x not of f x. And the last technique that we discuss is called proof by counter example. To show that for all x f x is true, to show that for all of f x is false, it is sufficient to exhibit a specific example C in the universe such that F c is false. So, suppose I have a proposition for all x f x. Now, what we can do is that we may search for one instance in the universe such let us call it C, such that f c is false. Then of course, for all x f x this proposition is false. This is called proof by contradiction. Now, we will move on to an example of a proof by exhaustion and a proof by contradiction. Now, suppose we would like to prove the statement there exists no rational roots to the polynomial p x equal to 2 x to the power 8 minus x to the power 7 plus 8 x to the power 4 plus x square minus 5. Now, of course, if we have to exhaust the whole set of rational numbers, we will not be successful because the set of rational numbers is infinite, but we can invoke a theorem called rational roots theorem, which says as follows. If p x equal to a 0 plus a 1 x plus and so on a n x to the power n is a polynomial with integer coefficients then any rational root of p x has the form a by b, where a comma b are integers such that a divides a 0 and b divides a n. If we use this theorem to the polynomial under consideration, then we will see that our universe reduces to only plus minus 1, plus minus 5, plus minus half and plus minus 5 by 2, and we can evaluate the polynomial p x at all these points and see that p c is not equal to 0 for all c belonging to u. This is where we are exhausting all the choices by reducing the universe, and in this way we are proving that there is no rational root to the polynomial p x. The second example that we discuss is an example of proof by counter example. Now, let n be a positive integer and define p n to be the partition function Now, a partition function on a positive integer is a function which gives the count of the number of ways that integer can be written as sum of positive integers without taking order into account. For example, if we take p 5 is 7. This is because 5 can be written as 1 plus 1 plus 1 plus 1 plus 1, 2 plus 1 plus 1 plus 1, 2 plus 2 plus 1, 3 plus 1 plus 1, 3 plus 2, 4 plus 1 and 5 itself. So, there are 7 ways of writing 5 as sums of positive integers, and therefore, we write p 5 is 7. Now, if we do calculate p values of from 1 onward, then we will find that p 1 is 1, p 2 is 2, p 3 is 3, p 4 is 5, p 5 is 7. Now, suppose we form a proposition from this, that is, for all positive integers n, p n is prime. Suppose we are asked to prove or disprove this proposition, then what we do is that we start from 6 onwards. So, if you see p 6, you will be able to see that p 6 is 11. So, we can't say anything, but then if we calculate p 7, we will see that p 7 is 15 and 15 is not a prime. Therefore, there exists positive integers such that the partition function on it does not return a prime number, and therefore, the statement is false. Thus, the proposition under consideration is false. This is an example of proof by counter example. The counter example is the number 7 whose p value is 15 and which is not true, which is not prime, and therefore, the proposition is not true. We stop here today. Thank you.